Hello, everybody. Welcome. It's my pleasure to introduce today's seminar speaker. Julia Steenberg is a Phanerozoic geologist with the Minnesota Geological Survey. Julia has a bachelor's in geology from Gustavus Adolphus College in St. Peter and a master's in geoscience from Idaho State University. Julia's research interests include geologic mapping and modeling, sedimentology and stratigraphy, hydrostratigraphy, and structural geology. Julia is a member and past president of the Minnesota Groundwater Association and currently the president of the MGWA Board of Directors. At least that's what it says on your bio. Today, Julia is going to be speaking about her research into the record of an ancient meteorite impact buried beneath the Twin Cities in Minnesota. So take it away, Julia.
All right, I just put this or just leave it here. All right, thanks, John. Thanks for coming. Thanks for the interest. I'm happy to be here today. I didn't have to come too far over from the Geological Survey. So I'll just start out by talking a little bit about MGS and our mapping, and then I'll go over the regional and local geology of sort of Minnesota to the Twin Cities to right kind of near the zone of the crater structure. And then I'll talk more about all the specifics of the crater after that. It's kind of nice to sort of lay out what the stratigraphy should look like, and before you kind of got to know the rocks a little bit before you see how much of a disturbance it really is. And so we'll talk about the subsurface data. The structure is totally buried. Nothing to see at the surface there, but if you were to go to the surface, you would be at the Pine Bend Scenic and Natural Area. They're owned by the DNR, looking out at the Mississippi River. We'll talk about the shock quartz we found, some initial crater interpretations based on our limited data set, and we'll go over some possible field evidence and some future directions. So MGS, if you don't know, we are part of the School of Earth and Environmental Sciences. We are off campus, not here in Tate. You can find us there about a block north of University on Territorial Road. We have an office. You can come in, you can look at our box, you can buy our publications or talk to a geologist. That's where we are. And all of our publications and maps and reports are available through, are hosted through the library's digital conservancy. So as you can see there, if you can see, all 804 apparently are on there right now, everything dating all the way back to the 1800s. You can find scanned and reported there. The main mapping program we do at MGS is called the County Geologic Atlas Program. It's been around since the late 1980s, early 90s, and it's basically a comprehensive study of the geology and groundwater resources of a county. We investigate the MGS, we investigate the geology, we produce maps and GIS publications, and we describe the geologic framework all the way from the very superficial materials, the quaternary landforms, down through the quaternary package and then into the bedrock layers below that. So it's a systematic series of maps that describe all of the subsurface, and we kind of produce paper maps. We also are moving beyond the paper maps. We produce a lot of GIS products, sort of these rasters and things that can be modeled and work with to be used for planning, environmental protection, and so on. And the MGS partners, what we produce is called Part A. Part B is produced by the DNR. They investigate the groundwater chemistry, groundwater quantity, and pollution sensitivity. So it's kind of sold as one big package. And that's our status, where we're at, completed in red there, and where you can see in the yellow is where we're mapping currently as of January. And our strong supporters are the Environmental Natural Trust Fund and the Clean Water and Legacy Act, among a few others. So Minnesota, if you ask me, maybe gets a bad rap from some of my friends who work in other states, but I think we have a wonderful geology, a wonderful geologic record, all the way, dating back to 3.5 billion years. We've got the Precambrian rocks to the north, and then we've got the Paleozoic sediments off to the, I'm going to use this pointer, I guess. This, yeah, whoops. There we go, pressing buttons. Then we've got the Paleozoic rocks in southeast Minnesota, deposited within the Hollandale embayment. And then we've got a series of Mesozoic, mostly Cretaceous, some Jurassic rocks off in western Minnesota, mostly southwestern Minnesota. So the sequences I'm going to be talking about today are the Paleozoics. That's where this record of crater exists. So looking at southeast Minnesota here, here you can see we're slowly, steadily filling in these counties at this 1 to 100 scale, basically formation scale mapping. The sort of grayed out areas are places we have yet to go with our 1 to 100 scale mapping. The colors sort of probably are not what you're used to seeing or hard to see, but basically the Cambrian rocks are in the lower part of the section. That'd be the Jordan Sandstone all the way down through the Mount Simon. So those occur, this is an embayment or a basin. So those occur along these edges here. And then above that, we've got the Ordovician sequence. That's a lot of these blues through here. The Prairie du Chien sits above the Jordan. I'll talk about more of these rocks in detail as we go. And then the younger rocks are later Ordovician series. And we have a little bit of occur through here. And then we have a little bit of Devonian just in the southern part of the state. So as you can see, it's a package of basically 3 main rock types: carbonate, coarse sandstones, and fine-grained sandstones. And that's the lithologies keyed out there. So if we zoom closer into the Paleozoics in the Twin Cities, basically going from the 7-county metropolitan areas keyed out here and we're looking at that sequence here. You can see the urban area of the Twin Cities. We have Paleozoic rocks as young as what's known as the Cummingsville Formation, that is Ordovician, and then we've got St. Peter, Prairie du Chien, Jordan, all the way down through the Mount Simon there too. So there you can see them keyed out, and it just, you know, for basic purposes, it's a basin in the Twin Cities. The younger rocks are in the center, and the older rocks are alongside of it. Here you can see a basic cross section just across from west to east, laid out like so. And Precambrian rocks are below that sequence. We use a lot of, you know, all of this, as you can see here in this cross section, is the rocks are generally covered by a lot of glacial material, right? You don't get a lot of outcrop to work with. Occasionally you do along river valleys and road cuts, but it's primarily covered by glacial sediments. And so we have to use a variety of different subsurface data, and I'll go over some of that in a little bit. And one of those would just be a geophysical log, is what you're looking at here. And those are correlation tools that we can use to map out formations and correlate from place to place. Oh, and the crater, you can see that here too. I forgot all about that. That's got the guys right here. Pine Bend impact structure is what we're currently naming it, and it is just 15 miles away from where we're standing today. The Twin Cities Mesoproterozoic geology, the rocks beneath the Paleozoics, those are generally mapped in 3 different formations, but a lot of times we lump them all together as just rift sediments. They're sedimentary rocks consisting mostly of what you see here in these photographs, largely reddish brown mudstones and siltstones. They have a variety of lithic fragments and feldspar, so they're not as mature as the Paleozoic sandstones that are mostly quartz. And they occur interbedded with mafic volcanic rocks. And then if you look at the smog image over the Twin Cities, you can see where a lot of the volcanic rocks exist. They're generally right along what's known as the St. Croix Horst, right through here. So that's where you see the basalts. So Dakota County, which we'll be talking about more in depth right here, and the crater area we're talking about is right here. And so it is close, but not on one of these. It is close, but not right next to one of these basalts. Okay. Come on. Here we go. So we talked about subsurface data a little bit. If you zoom in to the northern area of Dakota County, here's that little key with that 7-county location and the view that you're looking at here, there's a lot of data to work with, right? It's urban, it's residential, it's industrial. There's a lot of subsurface data near this site. And some of this data includes what's called drill cuttings. This is what drill cuttings look like. They're housed in these little envelopes in little boxes, all in our warehouse. We have around 8,000 of them now, I believe. And you can open them up, lay them all out, and see the stratigraphy at depth. So those are collected by drillers and then donated to the survey. So we have a lot of those. Those are these sort of plus signs, yellow plus signs on this map. And just the small black dots, those are just water well records. Anytime since the 1970s, a water well gets drilled, it's required that the driller fill out a water well record and describe what they encounter at depth as they're drilling. And so we use a lot of that. Most drillers are pretty good at describing the materials they're drilling through. And so we use that a lot for our subsurface data and our mapping. And here's another example of a geophysical log. The geophysical logs in the area, if you can see it, those are the thin black squares. So geophysical logs paired with the cutting set is a really nice key piece of data we use a lot for stratigraphic studies. So there are outcrops, not that many of them, but you see they occur mostly along the river valleys, and then some to the southeast part of the county where there's thinner glacial materials. We've got outcrops in Dakota County. From the uppermost outcropping is Decorah Shale. That's Lilydale right there, if you've ever checked that out. And then we've got a lot of Platteville, Glenwood, St. Peter exposures along these river valleys that you've likely seen and are familiar with. If you go further down the Mississippi Valley through here, kind of heading down towards Inver Grove Heights, off towards Hastings, then you'll see a lot more Prairie du Chien. And then there are just a few places where the uppermost Jordan is exposed, kind of near the Hastings area over here. So some of these other rock types as you go lower that aren't exposed, here's just a few examples of what they look like. The St. Lawrence is sort of a dolomitic siltstone, it's kind of gray rock you see there. The unit below that is the Tunnel City Formation. That's a fine grained sand, glauconitic sand. Here's some more glauconitic sand, and the Wanawak sandstone is the sandstone below that. So these samples are kind of representative of this part of the section, St. Lawrence, Lone Rock through the Wanawak. You kind of can see how the Wanawak sands are those low gamma signatures, and those fine grained feldspathic units are more of a high gamma signature. Next unit's down, the Eau Claire Formation. Here's some examples of the Eau Claire. It's a pretty good shale to siltstone. And you can see the high gamma signature from the Eau Claire. And then further down, the Mount Simon below that, here's some examples of the Mount Simon. It's mostly a coarse sandstone. It does have some shale interbeds in the uppermost part. Okay, so putting together the data, making a geologic map, it's pretty straightforward when you have this standard set of Paleozoic rock types that you know occur in a predictable stratigraphic package. And they have, for the most part, fairly uniform thicknesses at depths too. Wasn't that long ago that we mapped Washington County, that's just right over here. So we were kind of expecting to see something similar. We also mapped Hennepin County just over here not that long ago as well. And for the most part we did, but I kept shying away from this one area that I just couldn't make a whole lot of sense of. So here's kind of the data laid out of sort of the regular spread of data, and then I've highlighted in green sort of the anomalous data, or data that didn't quite fit, and the stratigraphy was either up or down from where it should be, or kind of non-distinguishable. And if you looked at the aerial footage of that area, this is kind of what it looks like. It's right north of the Coke refinery, and it's right adjacent to the Mississippi River. It is in an area where there are truck stops, landfills, and also residential housing. So that's the site. And Highway 52, it goes right across the middle of it. So you've probably driven over it many times. So let me show you some of those gamma logs first. So here is that circle. So if that's not clear, that I'm going to zoom in a little bit further. Okay, we're going to zoom in right through here. And so going from west to east, here's the logs. These little squares are just probably barely showing up there. My screen's a little smaller. But what's lining the figure on either side from west to east is our normal stratigraphic package. Gamma logs paired with cutting sets where the Prairie du Chien's on top, and then we've got Jordan, St. Lawrence, Tunnel City, what should be there, right? You can see how well those correlate together, right? From here to here. And it's all aligned based on elevations. So I've got, I don't know, 7, 8 wells in the middle here. These are the gamma logs that exist basically within this zone, kind of just pieced together. And you can see they don't really work, right? It took me a while to come to that conclusion, but you know, for a lot of times you want to take one, you want to maybe move it up, maybe you want to move it down. You can see sort of, well, this might be that part or that might be that part, but then I have to turn one around and that doesn't make any sense. So there was a lot of gamma log maneuvering and playing with, and finally we just said, something's going on here, right? And the ones with asterisks are the ones that we do have drill cuttings for. So I'm going to show you some of that data in a minute here. And actually right away here. And so here you can see we don't have drill cuttings for all of them, just these 3. So I'm going to show you this one and what these cutting sets look like. This is what we call number 704. It's the 704th cutting set we have out of our 8,000 examples. Okay. So here's 704. And so in gray, I sort of have what should be the expected stratigraphy. We just kind of correlate based on those logs around it. So we should have Mount Simon at depth with our typical Eau Claire, Wanawak sequence, Tunnel City, St. Lawrence, and Jordan. But this was troubling, right? How do you get, you know, the Tunnel City should be all this fine-grained feldspathic unit. It should have a nice high signature. Is this really 200 feet of Wanawak sandstone? So we scratched our heads a bit at that for a long time. And the more we examined the samples systematically, laid them all out, this is what we found. The lowermost portion is a dark gray carbonate-rich shale. The gamma log cuts out down here, but this sample is from this depth. Above that, in this interval, you have micaceous red to green shale. Dark gray carbonate-rich shale, siltstone, even I think it's partially limestone in some cases. That's never really been documented in the Mount Simon before. The red to green shale, you could get a little bit of it, but it's definitely not extensive in the same in the Mount Simon. What should be there is coarse sand, right? And then above that, we've got some very fine-grained glauconitic sandstone. And then we've got some dolostone with some minor glauconite above that. And then we have this, get into this sequence with this, you know, what's typical mature quartz sandstone, you know, nice translucent grains of clear quartz. And then above that, we're getting another sample that's sort of similar to what's below this dolostone with some minor glauconite. And then we're getting into the very fine glauconitic sandstone. You can see these tiny specks within this quartz grains. Hopefully the pictures are showing up okay for you guys. That's glauconite grains. And then above that, more glauconitic sandstone. And then above that, more glauconitic sandstone with these bigger black specks that are actually phosphatic brachiopods that only occur in some certain parts of the section. So again, we were working through this during the pandemic. We were home, we weren't in the office, but I corralled my co-workers together to look at a lot of these samples, to come in and look at them with me. And the lead geologist of the Minnesota Geological Survey looked at my samples, and this was his interpretation. And it took me a while to come around to it, but I did. This is what we think we're seeing. So if you just took the samples and you ignored how they should be in sequence, one was kind of hinting at this. These glauconitic sandstones are what you'd see in the Lone Rock, as well as those phosphatic brachiopods. The dolomitic siltstone, that's of St. Lawrence facies. This coarse find, of course, quartz sandstone. It really doesn't even look like the Wanawak, which is usually has more pyrite in it. It's not as white, and it's coarser. And if you're not familiar with the sequence, what's happening here is we're getting rift sediments where we don't think we have any Mount Simon. Then we have a little bit of Lone Rock, St. Lawrence, and then we have an overly thick Jordan with stratigraphically lower units above it. So we believe this cutting set is overturned. And you can actually stare at the gamma log and almost convince yourself of this too. You took one and flipped it over and laid it all out. We've done that. Okay, so I guess I said, thanks, but you're crazy. But no, it took me a while to come around to this, but the only one time, I mean, we don't see faults in Minnesota, right? They're there. The Paleozoic rocks aren't perfectly flat. They are faulted and there's structure to them. From Barn Bluff. I don't know, your default speaker has changed. I'll just let that do its work. So here's a picture of it from a long time ago when the trees and vegetation were removed. And you can see that green sandstone juxtaposed up against the tan. That's the Tunnel City Formation juxtaposed up against the Jordan Sandstone. So faults do exist. This is a classic place to bring structure students in the area. And you can still see it as you drive south on Highway 61 there. It's right along the road. For the most part, when we do see faults or when we do map them based on subsurface data, they're almost nearly vertical, and they occur in certain places that are overlying older rift faults. Okay, and so this section where we're at doesn't quite fit that bill. And so, but neither does how do you get a recumbent fault in the middle of the Twin Cities Basin? That doesn't really happen either, right? So I'm going to show you one more. I'm going to show you this one now. We refer to 3240. And this one's right in the center of what we're calling the crater. Okay, so take a look at this one. This right out of the box didn't look normal. You don't usually see these dark red colors in any of the Paleozoics. So at a closer look, I'm going to show you similar slide here as the last one. So the lowermost samples are this light gray color of these there should be Wanawak at this elevation regionally. There should be Tunnel City above that, and there should be St. Lawrence and then Jordan. But instead, this is what we see. We see at the base, we see glauconitic sandstone with some of those phosphatic brachiopods again, and a signature, a gamma signature that supports that, but that shouldn't be there. It should be Wanawak sandstone. Above that, the samples are fine to very coarse grain, pebbly quartz sandstone, coarse enough where we think when you get pebbles that coarse, when you get sand grain that coarse, it's usually the Mount Simon. So that's our working hypothesis that this is Mount Simon quartz above that. And then above that, we're into that red interval, and it does appear that that's feldspathic, pebbly sandstone. It looks like there's rhyolite. It looks like there's basalt pieces in it. It's much more like what we call that red clastics or those Mesoproterozoic rift sediments than anything else. And above that is sand that looks a lot like, well, that looks like this. It's cloudy, it's a little milky looking, it's not clear quartz. And so we're going to take a closer look at that. And that quartz, here you can see what it looks like a little bit more close up. Here's the more white looking grains against the normal translucent grains. And there's normal grains and there's white grains. It's a mix in this interval. They do appear to be densely fractured, and they're common not only in that uppermost interval, but the more we looked, we were seeing some of these quartz grains down lower too. Again, this was the charge led by Tony. He goes, well, this is shock quartz, this is a meteorite impact. And it took us a while to come around to that idea. But Tony said, well, look, here, my friend from Iowa Geological Survey just published this paper on the Decorah structure. And these are St. Peter sand grains. And here's a beautiful, nice translucent St. Peter sand grain. And they were seeing similar things, fractured quartz grains. And those do have PDFs, and they've since documented this structure in Iowa as the Decorah impact structure. So these fractured sand grains do occur and are associated with impact structures just nearby in Iowa. So we sent our samples off. You know, we're a mapping agency. We are not experts in meteorite craters. I'm not, and we are not experts in shock quartz. So we needed some strong expertise to look at these and make sure we're really seeing what we're seeing. And so here's some initial thin sections we had made, and you can see I've sort of blacked them out to help your eyes, but there are 2 to 3 preferred orientations in these grains. So these are tiny fractures that occur in these sand grains, and they're pretty planar and straight, right? They're not curved. And some of them, here's another one with 2 to 3 orientations, and this kind of cloudiness along it, that dark cloudiness, that's actually decorated with fluid inclusions, which is also something you can see related to shock quartz. So our experts were pretty excited. We asked Yui Reimold, who's now at the University of Brazil, and Ludovic Ferre with the Natural History Museum in Vienna, take a look at these. They immediately wanted us to send them some samples so they could get better, higher quality thin sections made to do more microscopic analysis on the grains themselves. And they're working through some of that right now, but they are very planar, they said. They have 2 to 3 sets of preferred orientations, which you saw, and they are very closely spaced in some grains. They did some of this double polished thin section analysis, and I'll show you their pictures in a second. Well, I will now. So here's some of the pictures that came back initially from Ludovic, and he said, yes, you've got these planar fractures. Those are the ones on the left, and those are a little bit further a space. Those are 15 to 20 microns apart, and then the other ones, those are known as planar fractures, but a shock quartz, there's a few different ways to shock quartz, right? And if you just have planar fractures, apparently there's other ways to make planar fractures in quartz than just a meteorite impact. But the smoking gun for meteorite impacts are what are called these PDFs, or much closer spaced, areas of narrow individual planes of fractures, and that's this image on the right. So we do have several examples of PDFs in some of the quartz grains that they've documented. And some of them are decorated with fluid inclusions as well. And this one was, they thought this one was pretty neat. This is a feather feature, what they call shearing along the planar feature. So that's some of our earlier images that document the shock quartz in this sandstone. Another piece of the puzzle here is in that first well I showed you with the overturned beds, there's a lot of these little fragments of black glass. And we've never really seen little fragments of black glass in cutting sets that we've examined over the years. So this was a bit of a first, but we weren't really sure what we were looking at. They are real small, but they occur throughout the section, kind of intermixed with that sandstone. I guess our hypothesis or our thought was, could this be related to impact melt glass? Josh kindly took a look at them and said that there aren't really any magnetic minerals in them to suggest that they're related to the meteorite that hit, but that's not really conclusive one way or the other. It could still be related to the impact. Some results that we've just gotten back from SEM show that the composition sort of lies within the basaltic andesite realm. So we're still wondering about these and sort of their origin, but it's nice to know that they are in the basalt realm. Maybe they came from the basalts at depth in the structure, I guess, is our working hypothesis. So let's start putting it all together. Here's the geologic map that I've come up with for this location in northern Dakota County, and then you can see the Washington County map just kind of right alongside of it too, so you get the full picture. So again, we're adjacent to the Mississippi River. It's associated with a buried bedrock valley that cuts right through it, which again is sort of another geomorphologic question, a mystery that yet to work out. You know, did one cause the other or what? The whole site is buried by anywhere from 30 to 120 meters or 100 to 400 feet of quaternary sediments. And there are 5 cutting sets and about 13 gamma logs we're using to kind of delineate the stratigraphic disturbance, and a handful, 30 plus water well drillers descriptions that are really not normal for the area either. There's a lot of descriptions that are red. There's a lot of descriptions that are blue sand rock, and just things that you just don't typically see in water well drillers descriptions, but hard to base much off of that anyway. But those do appear to be really odd around that area. And then, so we mentioned the mid-continent rift and those reactivated Paleozoic faults, and those all occur right through here. So they are only about 6 kilometers away. But again, those are typically just, you know, your traditional normal fault, near vertical, that's affecting the Paleozoic rocks, nothing that causes them to become overturned. So if we look at it in cross section, yeah, okay. So going from north to south here, this cross section is showing, you can see that the area, this inner circle is about 4 kilometers in diameter. And sort of that outer, more disturbed area that we really want a lot more, we want some more data before we really know what's happening there, but that's about 8 kilometers. And there's as much as 575 feet of this mixed sandstone, siltstone, and shale samples that we have from cutting sets to work with. So you kind of see how it lays out here. Here's this one with the shocked quartz, and here's the one with the overturned bed and where they're sitting in terms of elevation within the normal stratigraphic package. The ones with the shocked quartz have that asterisk there. So you can see the upper sequence is removed by erosion from this bedrock valley. So it's difficult to understand the timing of the impact. Our running hypothesis is that it's as old as Late Cambrian because that's the age of the Jordan Sandstone that's overturned. And then there's apparent lack of carbonate from the Prairie du Chien. The Prairie du Chien is this blue formation that occurs through here. We don't see any Prairie du Chien carbonate in any of the sample. So that's kind of how it looks. To give you, a little bit, when we make a geologic map, one of the first things we do is map out the surface that we're working with, sort of the bottom of the quaternary package and the top of the bedrock. And the next map we make is a contoured surface of a certain stratigraphic formation. Usually we choose the Jordan Sandstone because there's a lot of data associated with it. And drillers are pretty good at describing the change from the carbonate to the sand. So you can kind of get a sense of that, the elevation of the top of the Jordan Sandstone. Clearly it's affected by the faulting related to the rift. But if you look up here, there's just some oddness where that we're getting some of the data is suggesting that there's a little bit of a drop down by 25, 50, 75 feet at times that kind of occur around this zone of the crater. So when we talk about forming a crater, there's really 3 stages, right? There's the initial contact and compression. The average collisional velocity of the impactor is about 7 kilometers per second. And that only takes several tenths of a second to, blow out the initial crater. Then there's the excavation stage, sort of the dissipation of that shock wave and the opening up of the cavity. And then there's the modification stage where it sort of gravity drives the collapse of this initial crater. And depending on the degree of modification, craters are sort of are classified into simple versus complex. And simple would be just kind of your standard bowl-shaped, bowl-shaped crater, like this, like you'd see Barringer meteorite crater if you've been to that in Arizona. And then there's the complex crater, which you can see has these terraced rims of drop-down stratigraphic intervals, and there's a breccia-filled center, and what there also is an uplifted center. And that's what we think we're seeing. So if you look back at this cross-section, again, it's limited data. We're actually really, I'm grateful to have the data we have. It is actually pretty rare to have this deep of data and this much of it in any given area, in this, small of an area. But so we're happy with the data we have. But, as you can, if you squint your eyes and kind of believe it, right? We've got Mesoproterozoic rocks that we think are up high in the section that should be down here at this elevation. Maybe that's part of a central uplift. And then we've got what we think are overturned beds, and those occur kind of on the other edges of that. And then they're also, at least this one is dropped much further down in elevation than where it normally should be. So that's what we're working with in terms of the data. So there's a lot of, there's some calculators out there where you can estimate, okay, what was the size of, this space rock that hit Invergrove Heights possibly 490 million years ago. And so you can do some, based on some, with a known crater diameter, if we kind of go with the 4 to 8 kilometer diameter, sort of known rock densities for sort of porous sedimentary rock. And we're basically estimate the size of the space rock was about 150 to 600 meters. So a football field or 3, right? So that's the size that we're working with. So I mentioned a little bit at the beginning about some possible field evidence. So if you look back at that outcrop map, the only places where there's Jordan exposure are down here, but that is only about 10 kilometers away from the crater. And well, I should say the first thing we did was open up every cuttings box again for the second time within an 8-kilometer area of this site, and didn't come up with a single other shock quartz grain. So that was a bit of a bummer. But when we scoured some of these outcrops, we really weren't, this was early when we really weren't expecting to see much related to the impact structure. But take this one, for example. This is an exposure right here, so not that far away. This is Oneota exposed. So you're looking right at the Cambrian Ordovician contact. This is Oneota, and this is the Jordan Sandstone. And what we found was kind of interesting. You kind of already see, right? This bed that's about a foot thick is not real. It's not well bedded. It's pretty mixed up. It's got it's more of a conglomerate than anything else, and it's got some bedding here. I got another one zoomed in. Yeah, maybe it's hard to tell, but you can kind of see some of this bedding kind of goes up, and then it's kind of all over the place. What's in that interval is a lot of pebbles. Pebbles are common at the top of the Jordan Sandstone. It marks an unconformity before the Ordovician sediments were deposited on top of it. But the more we looked around at these pebbles, we thought they were a fairly, I don't know, they were more unique lithologies than we're used to seeing. It's mostly just quartz and chert lithologies at the top of the Jordan unconformity. And one of the pebbles, just one, had these interesting lines through it that looked fractured. So we thought, what the heck? We'll send it off to Ludovic. And sure enough, that's got some PDFs in it too. So it's one pebble, but here we are scratching our heads. One more little piece to this puzzle. Is this ejecta? Is this related to the impact? If it is, it supports the latest Cambrian, very earliest Ordovician age of the impact, which is pretty exciting, a time when clearly we were closer to the equator and a beach-like environment. So how does this size up to other regional impact sites? We do have impact debris all the way over here in northern Minnesota from Sudbury, that 1.8 billion-year-old impact that occurs in Canada. But this would be Minnesota's first known meteorite crater occurrence. There are some not in our neighboring states, right? Just over the border in Wisconsin, there's Rock Elm, and there's the Decorah structure we talked about, and the Manson structure in Iowa. And these, range from crystalline targets to Paleozoic strata targets. Not one of them is right at that 490 million-year-old age, so they are of different ages than what we think we have. And a lot of them occur at this sort of late Ordovician time period, this 480 or so time, when it's sort of a known interval when there are a lot of meteorite or crater occurrences in the world, and it's just from a breakup of an asteroid body at that time during the Ordovician. So we kind of thought, hey, it'd be cool if this was part of that late Ordovician age, but it doesn't appear to be so. So again, how does this stack up? There are only 200 confirmed global 200 confirmed craters on Earth per this Earth impact database, and they range from just several meters across to giant 160-kilometer diameter structures. So our 4-kilometer diameter structures on the small end. They range in age from just recently to 2.4 billion years old. And about a third of them are totally buried. So about 2/3 of them have been found because they've seen something at the surface. A third of them are totally buried and in the subsurface. So there's been some calculations based on how often craters are produced and Earth's average erosion rate, and they've estimated that there are still several hundred more small craters that remain to be identified on Earth in that 6-kilometer or less zone, but that the large ones are likely accounted for. Just the density along this line is higher than the ones here. So maybe, so that's exciting, right? Maybe we found one of these smaller ones that are not accounted for yet. And, new findings are significant for impact science, obviously, and they further the understanding of the mechanisms by which they produce the geologic and biological effects. So we're pretty excited about this. In terms of future analysis and study, as a mapper at the MGS, I get a little bit of time to do research and go as far as I want with things, but I don't have a lot of time. So we're always actively looking for students, collaborators, or other interested parties to work with us. There's some analogs and models we'd like to make with sedimentary sandstone target rocks. How many craters do we have examples of that where it hit a sandstone beach? So we'd like to look more at that, sort of find some analogs. We'd like to investigate more of the geophysical methods. Aaron Hirsch is a geophysicist with the MGS now, and he may be able to do some more gravity measurements in the future, which would be really interesting and shed light on the structure, hopefully. I have, my pie in the sky dream is to get some more material to work with, and that would have to be done through some drilling, obviously. So we'll see if we can track down some funding to get a core or 2 or 3 in the ground. If we could just get a little bit, that would be great. So we're actively looking into that right now. And, I think there's a groundwater story to this too. I have interest in groundwater. And, there are, if you look at it, this is a plot of the water wells in the state of Minnesota and how many occur over this structure. And there are 650 wells overlying the structure. Some of them supply water to businesses, some supply water to homes with multiple people, obviously. So I think it's worth looking into in terms of groundwater. Some impacts are known and associated with elevated levels of salinity or fluoride and sulfate and that sort of thing. So it's just another avenue we look to maybe go down in the future. So I think I'll stop there and happy to take any questions or discussion.
Great, thank you, Julia. The tradition here is to open the floor to student questions first. So if there are any online or in the room, go ahead and raise your hand. Great.
Hi, thank you so much. It's super interesting. On your maps where obviously some of the crater like runs over the edge of the Mississippi River, how are you like guesstimating where to draw that line? Because it looks like obviously you don't really have well data in the river.
I just drew a circle. I have no data. I have no data. Most of the time craters are around. That's really all I got. No. Okay. There is some data, you know, one thing I'm hoping to do is we have what's called a passive, well, we can do passive seismic. That's a little tool that goes on the ground, geophysical tool that can, where we can get the depth to the rock. We can't get any structure or information past that first interval, but we do hope to fill in some of those gaps along the river with a little bit more passive seismic. So we can at least get a topography. Not that that will help a whole lot with delineating the crater, but yeah, that's just a total line I drew.
Great, we've got one online from Jen. Listening from England, I'll be joining, let's see. I was wondering which scheme for shock was used in this study. There have been some recent updates that consider the target lithology. Similarly, do you see shock effects or anything else unusual in any of the minerals other than quartz that could be related to impact?
Yeah, that's something we need to keep looking into. I was having a discussion about something of that earlier. I'm not able to identify schistosite or the coesite or these other things. I think you need I would need to seek out somebody who would be able to help me identify those things and then look for more shock quartz, but that's definitely something we could do. Right now, all our thin sections are currently in Vienna, but that's a good point. Yeah.
Any other student questions? Okay, open it up to anybody with questions.
Yep. Oh, back there.
Wouldn't there excuse me, sorry, wouldn't there be any kind of like geochemical evidence that you could look for, like iridium or any of those other heavier elements?
Yeah, and I think that's why we need more material. Is there's very little material left in the cutting samples that I've shown, but yeah, I would like to do some whole rock analysis and look for iridium. I think maybe we'd try that one with the shock quartz first rather than the overturned beds, but that would be a great avenue. Good support for the crater evidence. Yeah.
So the overturned beds are parts of the stratigraphy as blocks that get inverted during the crater formation process. What's the explanation for the overturning?
Well, I think it's just the shock. Let me show it from the pressure. So you can see it when it hits and then it just blows those up and over. So at overturned beds, I think, are found at a lot of different crater sites, but at Barringer or Meteor crater, you can actually see them just right on top of the other. And they usually are along those edges of the rim. And so what I think we have is sort of an edge of the rim, but then it's also been dropped down, possibly.
The Manson and I
Yeah, ejecta flaps is the term. Yeah.
I had a super simple question. On the maps that you were showing us, there was the circle, but then there was a sort of adjacent thing next to it. What was that?
Yeah, I probably didn't spend a lot of time talking about that. So this is an area where I was able to map the rock, right? You see colored formation polygons there. So I see Prairie du Chien and Jordan, but it appears to be a drop down and at different elevations than it should be. And there's also times where it's brought up. So like it was mostly drawn based on the elevation of the Jordan top. So this low is where the Jordan is a little bit lower than right next to it where it should be. So how it's related to the crater, I don't know. It'd be nice to have some more cutting sets or data in that area.
Questions online or in person? Okay, well, let's thank Julia again for a great talk and for joining us today.
Thanks.
Thank you.
Yeah.